Hi everyone. Let's just wait a few more minutes because it seems that we've only got 8 people in the chat right now. So I'll just wait about another minute. Caleb, seriously, people are getting sick at your work? All right, let's start. I do leave these live streams online, but it's still good to be here because if you have any questions in the lab, you can ask them in the chat, even though there is about a 30-second delay. But let's start. So today's lab is actually going to be the second part. It's actually a continuation of last week's lab. And I've already logged into our Moodle site. You know where everything is. And let's just go to Physics 102 here, Physics 102 112 lab. And the lab that we're going to be doing today is actually, so we're off a week because I skipped the thermodynamics, and I skipped it because it wasn't at all appropriate for for this kind of an environment. And so we're actually doing electricity number 2. I will be adding another lab later. Okay, I will be making up a lab, something that's actually more appropriate for a virtual environment. And the handout is right here. It's actually lab number 9, electricity number 2. Okay, and if you scroll all the way to the bottom here, I've got the typical summary of the lab, what I expect you to write up, and also some YouTube videos to watch. Okay. And admittedly, the very last one, these are pretty good. The very last one is not that good. I simply could not find a good video of people measuring the time constant of an RC circuit. If I literally had just 1 week in the lab, I could have recorded everything, and this would have been nearly perfect. But I have to work with what I have. Okay, so let's take a look at the lab write up, and I've also got some whiteboard slides that I'm going to show you because what's written up here, it's good, but you need a little bit more. Okay, and we are going to skip some of the things that are in here. All right, so let's go over it. Today's lab is actually going to be about 3 things. There is the series and parallel resistors. Okay, now we actually did that already. Okay, we did that last lab. And last lab we did series and parallel resistors, but we did the effective resistance of resistors in series and resistors in parallel. In this lab, we're also going to look at resistors in series and parallel, but we're going to look at the voltage drop across them. Actually, scratch the parallel. We're just going to look at the voltage drop across resistors in series. Okay. By next week, you're going to have all this theory, and you're going to see why the voltage drop across resistors in series is more important. Okay. And then we're also going to look at a new electronic component called a capacitor, and we're going to put a capacitor in series with a resistor, and that actually leads to a timing circuit. And this is actually a very important circuit, even in biology, because a lot of things in the human body actually act like RC circuits, okay, where there's both a capacitance, which I have yet to introduce to you, and a resistance, okay, and potential, that is voltage in the human body, is simply produced chemically. You know, things like nerves will pump, or all cells will pump sodium ions across their membrane, and by doing that, pumping means they just use these proteins to push the sodium ions out, and that actually creates little potentials across cell membranes. So this, even though we're looking at this in terms of circuitry, it has applications in many different places in the world. Okay, so let's start going through the theory here. There's a theory that Dr. DeHaven gives, and you can see there three resistors in series. And what we're actually going to look at this time is, we know how to calculate the effective resistance of resistors in series. What you do is you simply add up all the resistors, and you can actually see down here it says R eq, which equivalent. So our equivalent is simply the sum of all three of these. Okay, but what we want to do in this lab is we want to actually measure the voltage across each one of them. Okay, and so there's a voltage applied by a battery, and this is the symbol for a battery here, and these squiggly lines, these are the voltage for a resistor. And if you take a multimeter and set it to measure voltage, remember that a multimeter can measure three different things, at least three different things. It can measure voltage, it can measure current, and it can measure resistance. Okay, and so if you set the multimeter to measure voltage, and you put the probes, one probe over here and another probe over there, you're going to get a measurement of the voltage across that resistor. Okay, and Dr. DeHaven gives an analysis here, but let me actually switch to my whiteboard. I've given you a slightly different analysis there, and it might be a little bit more intuitive. Okay, you'll see something similar and in greater depth in my lectures anyhow. Okay, so let me switch here. So what you're looking at here is a diagram. The best I could do with my whiteboard and my mouse is basically a 10 volt a 10 volt battery right here, and there's a 2 ohm resistor there, and there's another 2 ohm resistor here. This little piece here in 5 volts there, I probably should have did it in a different color. That's not part of the circuit, that's just going to be a measurement there, and there's another measurement there. But the circuit continues from the battery through the 2 resistors and then back to the battery again. Okay, and the voltage here is 10 volts, and if you put the multimeter across the 2 ohm resistor and you ask what is the potential across that, you would find that it gives you 5 volts. And if you put it across the second 2 ohm resistor, you would find that it gives you 5 volts again. Okay, and it kind of makes sense because these are both the same size resistors, so there's no reason why one should be any bigger than the other. But like, why does it split like that? Okay, why does the voltage split like that? So one way to think about voltage is to think about it as a drop, like a height. Okay, but it's not a physical height, it's the equivalent of a height but in electricity. Okay, so over here at the positive end of the battery, it's like you're up high. Okay, and so you're like at the top of the hill, and then as you walk around the circuit like this and you come to the negative, you're at the bottom of a hill. Okay, and then this is like a steep incline, okay, where the electrons are pumped up back up to high voltage, and then they go around again. Okay, now if you're walking from the top of a hill and you walk to the bottom of a hill, then if you add up all the drops along the way, that has to add up to the height of the hill. In other words, if here you're at 10 volts high, and then you go down 5 volts, and then you go down another 5 volts, then you're back at ground level. Okay, and so the sum of all the voltage drops across all the resistors has to add up to the 10 volts there. Okay, it makes no sense. It's kind of like saying, I'm at the top of a hill and I walk down only 5 feet, and then I come back and I'm at the bottom of the hill, but the hill is 10 feet high. How can that work? Okay, so basically if you're at 10 volts here and you drop and then you drop again, if you add up all the drops, they have to add up to 5 volts. Okay, so that's the first point. Let me see if there's any questions in the chat here. Okay, it looks Okay, there's the whole point about the drops. Now, if this drop across the 2 ohm resistor and the drop across the other 2 ohm resistor has to add up to 10, and they're the same, it's kind of obvious that they both have to be 5 volts. Okay, so that was easy. But like, what happens if you've got different voltages? Or in Dr. DeHaven's lab write-up, he's got 3 resistors. And actually, in one of the videos, I found a very nice video that explains this theory. It's also 3 resistors, okay? And even actually, a professor did an experiment exactly like the one we would have done in the lab. And there's even numbers, so you'll actually be able to look at the numbers and verify them using this theory. So let's look at how you would do this if you have different resistors in there, okay? So here I just chose a very simple change. I took my 2 ohm resistor and I replaced it with a 3 ohm resistor. Okay, so I still have the 10-volt battery, and now the drop goes through the 3 ohm and then it goes through the 2 ohm and it comes back again. So we know that if you add up the voltage V1, which is the drop across that, and V2, which is the drop across a 2 ohm, you know that that has to add up to 10. But we don't have the symmetry that we did in the previous example, so we don't know how big V1 is and how big V2 is. Okay, now we do know what the total resistance is. That was the subject of last lab. The total resistance when resistors are in series is they just add. Okay, and so if you just add up the 2 resistors here, so you've got a 3 ohm and then you've got a 2 ohm, and so there'll be a total of 5 ohms. So the total resistance is 5 ohm. Now, the other subject of last week's lab was Ohm's law, and Ohm's law basically says that the voltage is equal to I times R. Okay, now if your total voltage through the whole circuit, across the whole circuit, is 10 volts, then for this V here, you're going to put in 10 volts. Okay, you don't know the current. That's actually what we're going to solve, and you're going to see why that current is important in a second. And then R, that's going to be the total resistance. Okay, so we rearrange this equation and we write it as I is equal to V over R, and that's 10 volts divided by 5 ohms total resistance for a current of 2 amps. So basically you would have 2 amps of current traveling through this circuit. Okay, and that 2 amps, remember, current is like a current, like a river. Okay, so if you've got, like, so many electrons passing through this resistor per second, well, then you have to have the same number of electrons passing through this resistor per second. Why? Well, if the electrons flow into this one faster than they flow out of that one, then they would accumulate here. I mean, just think of water. I mean, imagine if water were flowing into here faster than the water flows into there. Okay, like a bathtub. The water's flowing into the bathtub faster than it flows out. Well, then eventually, something's going to give in here because these electrons are accumulating. Okay, so current is the same all the way through this circuit. Okay, so whatever that current is, and it turns out to be 2 amps, that 2 amps is going to go through the 3 ohm resistor, and the 2 amps is going to go through the 2 ohm resistor as well. And now we can use Ohm's law individually to find both V1 and V2. So for V1, that's going to equal I times R1. Okay, so over here when we did V is equal to IR, we did the total resistance and had the total voltage. But here we have only the resistance R1 and we have the voltage V1. So we're just kind of looking locally here. And we're saying, what's the current through this, and what's the resistance here, and what's the voltage here? So that's V1. I is the same throughout the circuit, so it's still just I. That's a little dot there to indicate multiplication. Otherwise, it would have looked funny. And R1. And so you have 2 ohms flowing through there, and 6 ohms, and that gives you 6 volts. So the voltage drop across the, let me just scroll up a bit here. The voltage drop across the 3 ohm resistor, okay, that has to be 6 volts. All right. And similarly, if you do V2 is equal to I times R2, all right, well, then that's going to be 2 amps multiplied by 2 ohms, and the voltage drop across that one is just going to be 4 volts. All right. And when you add those together, they had better add up to 10, otherwise you did something wrong. And so you have 6 volt drop here, 4 volt drop here, 6 plus 4 is 10, and it works out. Okay, so there's the theory for the first part of the lab. And if you, whoops, I've lost this happens. There we go. If you go through Dr. DeHaven's lab write-up, it's the same thing. And I've also got a video on this, okay? So it's explained there as well. Now, that's the theory. And one of the things that you would have done in the lab is you would have verified the theory, okay? And you would have verified the theory by literally hooking up three resistors in series, applying 10 volts to them, and then using your multimeter to measure across the voltage across three of them. And you would have then added up the voltages. Well, first you would have checked, is the voltage what is expected by the theory, just the way I was able to calculate the voltage drop across the three resistors. You would have calculated that, and then you would have measured it and would have said, does the measurement fit the theory? If it does, then it's verified. If it doesn't, then it's not. And I've actually found a video which does exactly that, and it's exactly what I would have done in the lab if I were to try to demonstrate this to you, or what you would have done in the lab. Okay, so for this part, you can even give example numbers. Okay, now Dr. DeHaven does also discuss circuits in, we're not going to do the variable resistor. It's just a variation on the same theory. We're not going to do the parallel, okay? Because for the parallel, the voltage drop across all three resistors is the same, and so it's not that interesting. So that's one of the parts of the lab. Okay, let me look in the chat here if there are any questions. Okay, so that's, how we have different purposes for the lab. Well, that's one of the purposes. One of the purposes is to show that basically, let me go back to a diagram here like this. One of the purposes is to show that if you have some voltage that you're applying to a bunch of resistors in series, the voltage drop across all the resistors, if you add them all up, that has to equal the voltage that you're applying. And secondly, you can calculate those voltage drops by using Ohm's law locally on each one of the resistors. So this delta V3 here that Dr. D writes, okay, that's the voltage difference between this point there and that point there, okay? And that's got to equal the current through that resistor multiplied by R3, which is the value of that resistor. Delta V2, that's the voltage drop across the second resistor here, okay? And delta V2 has got to equal the current through that one times R2, which is that second resistor, and the same thing for the first resistor, okay? And so that's what we're verifying in the first part of the lab. All right, let me see if there's any questions in the chat. You guys seem to be doing okay. How many people are watching? It looks like 11 people are watching. Okay, good. All right, so second part of the lab is going to introduce another component, okay? And it actually looks like this. And it's what's called a capacitor. Okay, so we'll study all of this stuff in detail in the class, but what a capacitor does is if you apply a voltage to a capacitor, so there are two leads here, if you apply a voltage to capacitor, what will happen is that the capacitor will actually charge up. There'll be like an electrical charge. It's actually made of two parallel plates. Okay, and one plate will become positively charged, another plate will become negatively charged, and the charge will just sit there between the two. And so you've got this like mini storage of charge, and that charge then, if you attach the two leads together, the negatives can flow from the negative to the positive, and then the capacitor will discharge. So capacitors can be charged up. You apply voltage and they charge up. And then if you short them out, that is, you just take the battery out of the circuit and just attach the two, then they will decay down. Okay, so it's just enough to understand intuitively how these work. Okay, and by the way, they come in different shapes. There's some that are disc shaped like that, and then some that are cylinder shaped like that. Okay, now if you just attached a actually, let me go back to my whiteboard. All right, and let me switch to another image here. Okay. If you just attach the capacitor, maybe I should tell you first the symbol for a capacitor. So the symbol for a battery has a long and a short line, whereas the symbol for a capacitor is just two parallel lines like that, and they're supposed to be exactly the same size. Okay, so it looks a lot like a battery, but it's just got two parallel lines there, and they're both the exact same length. Okay, now if you just had a capacitor without a resistor in a circuit like this, batteries, ideal batteries, have enough current that they can deliver, that they can charge up the resistor, the capacitor instantaneously. Okay, so in other words, as soon as you attach the capacitor to the voltage, the charge just builds up on the capacitor right away. Okay, so that's okay if that's what you want, but we're actually going to create a timing circuit. That is a circuit that takes a certain amount of time before the capacitor charges up. Okay. Now the way we'll do that is rather than attaching the capacitor directly to the battery, we're going to put a resistor in the way. Okay, and by the way, this S is a switch, okay, because I'm going to have the circuit open at some point, and then I'm going to close the switch, and that's like t equals 0 when things turn on. Okay, so with this resistor in there, and imagine that the switch is closed, yeah, the battery wants to push electrons onto the capacitor like that, but the resistor is resisting that current, and so the capacitor can't charge up instantaneously. It's actually going to take some time to charge up. Okay, and so as soon as you close that switch, the capacitor starts to charge up, and then eventually it gets to fully charged. And that's what I tried to indicate with this graph here. Okay, so what you're seeing in this graph is Q, and Q is a symbol for charge. So Q is the amount of charge on that capacitor. All right, and the horizontal axis here, that's time. Okay, and that's supposed to be 0 seconds. It looks like I wrote OS, but that's supposed to be 0 seconds there. That's the time at which I close the switch. So before the switch is closed, I mean, the switch, you can think of it as having infinite resistance. It just does not allow any current to flow at all. As soon as I close the switch, the battery starts to push electrons onto the capacitor, okay? But because there's a resistor in the way, it doesn't do it instantaneously. It takes a little bit of time. And so what you can see here, the red line, is that the capacitor starts to charge up. At first it starts to charge up quickly, and then it charges up more slowly, more slowly, more slowly, more slowly, and then eventually it reaches a maximum there like that, okay? And so this is a characteristic curve for charge accumulating on a resistor, accumulating a capacitor in an RC circuit. So these circuits are called RC circuits because you have both a resistor and a capacitor in series like that. Okay, so let me see if there's any questions in the chat. All right, looks like you guys are understanding this. Now, this is the circuit for charging up the capacitor. If we take the battery out and close the circuit, then you get a circuit that looks like this. Okay. And so now you say, where did the battery go? Well, the battery's gone. But imagine that the capacitor already has its charge on it, okay? And that charge, as long as that switch is open, that charge has nowhere to go because the charge can't flow through the circuit. Okay, it would like to go from the one plate to the other plate. Suppose this is where the electrons have accumulated. The electrons have accumulated on this plate. They would love to go over to the other plate. They can't go through the middle because you've actually got what's called a dielectric in there. This is a material which doesn't conduct electricity. So the electrons on this plate right here, on the right plate, they would love to go to the left plate. They can't go through the middle. They go, well, we'll go through the circuit, but they can't go through the circuit either because the switch is open. Okay, so the charge would just sit there. As soon as I close the switch, the electrons go, oh, we can travel through here, through here, through there, through the resistor, and then get to the other plate, get to the positive plate. Okay, and then they're happy. But of course, because there's a resistor there, this can't happen instantaneously. If there were no resistor, then the capacitor would, discharge almost immediately. Okay, never exactly immediately because there's always some resistance in the wires as well. But if these were ideal circuits and there is no resistance in the wire, then all the electrons that want to move from the negative to the positive plate, they would just en masse move through there. But because there's a resistor there, the electrons, they can't go all at once, and they'll go through a little bit at a time, and eventually it'll get discharged. Okay, now if you plot the charge versus time, it starts up high, and we can call that high number Q naught. Okay, so Q naught is the total amount of charge that was accumulated on that capacitor before I close the switch. And as soon as I close the switch, the circuit is completed, and the charge starts to flow from the negative to the positive end. And you can see that the charge on the capacitor decreases, 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 and eventually it goes to 0 like that. Okay, so there it is, qualitatively speaking. Okay, so this is an RC circuit, and I'll tell you about this formula in just a second. But let me tell you first, where you would see an RC circuit. Even like the human heart has something like this, because the human heart is like has a pacemaker, and a natural pacemaker. And what happens in the pacemaker, or even an artificial pacemaker, works like this. Basically, through the biochemistry of the heart, charge will build up, and then eventually it's discharged, and that's what causes the heart to beat. So this allows for a kind of a timing. All right, because otherwise, how would you time things with electrical circuits? And this is a way that timing can be done. An artificial pacemaker is exactly an RC circuit, okay? And I'm just picking that as one of many examples. All right, so now you kind of understand why you get this red line in here, and you say, well, can we do a more rigorous mathematical derivation of that? You can. I won't even do it in the class, okay? But basically what you get is exponential decay. Okay, so this is what exponential decay looks like. You have that the charge at any given time, so Q here is actually a function of time. I didn't write the time function part of it, but just think of Q here as a function of time. It's basically this graph here, okay? And it's going to equal Q naught, which is the original charge, the charge at t equals 0, okay, multiplied by this exponential, and the exponential is minus t, and t is, time, and it ticks away, divided by this symbol here is tau, okay? And tau is what's known as the time constant. It's kind of a characteristic constant which describes how fast or how slow the charge will decay, okay? And it turns out that tau is actually just equal to the product of RC measured in MKS units. Now R in MKS units is ohms, all right, and we'll actually see this probably by Wednesday of next week, okay, and C here is actually measured in volts per coulomb, okay, and we'll see that next week as well. And when you multiply the two together and you do a proper unit analysis, it turns out that tau is just in seconds. So this is going to be seconds divided by seconds, but that's a constant, okay, and that's just a variable which ticks away as time ticks away, okay. Now, why does this function here represent that red line? Well, if you put t equals 0 here, then you've got negative 0 divided by tau. And tau is just a number. You can think of it as like 1. Okay, it doesn't matter. Okay, so you have like 0 divided by 1. And that's just e to the 0. And e to the 0 is 1. Or any base raised to the power of 0 is 1. And 1 times q naught is q naught. And so you start off at q naught. Now, as t starts to get bigger and bigger and bigger, imagine t is equal to 1 and tau is 1. So 1 divided by 1 is 1. E to the minus 1, e is about 2.7, okay? So e to the minus 1 is like 1 over 2.7. It's like 0.37 something, 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 okay? So by the time t is equal to tau, this thing has reduced to like about 30% of its original value, okay? And as t keeps growing, you get a e to the a more and more negative exponent, and q will become smaller and smaller and smaller. This number will become smaller and smaller and smaller. In fact, you can do this on your calculator, okay? Try e to the minus 1, then do e to the minus 2, e to the minus 3. By the time t gets very big, like it's about 10 or something like that, e to the minus 10 is a very small number, okay? In fact, if you do e to the minus 100, it's effectively 0, okay? Your calculator will basically underflow, all right? So what happens is it starts off at q naught, and it goes smaller and smaller and smaller, and it never exactly reaches 0. This is called an asymptote, but it becomes so close to 0 that like in the lab you would not be able to measure the difference, okay? And so that's basically the story of exponential decay, okay? So there's your exponential decay as a capacitor discharges. All right, so if everyone's okay with the theory, there it is for how a capacitor works. Again, just to recap, a capacitor is a device which can store charge when you place a voltage across it. Okay, if the capacitor has a charge and you close the circuit and the capacitor is forced to discharge through a resistor, it doesn't do it instantaneously. It takes a certain amount of time, and the curve, the shape of the curve is actually an exponential decay with a time constant which characterizes how fast that decay occurs, okay? Now, in the lab, what you would have done is you would have actually hooked up a capacitor and a resistor in series like that. You would have charged them up, okay? And then you would have shorted out the capacitor. You would have basically made the circuit. And as the voltage decays, you would have put your oscilloscope in this special mode called triggering, okay? And what triggering does is basically as the voltage decreases, when it decreases past a certain point, that's when it's displayed on the oscilloscope. Otherwise, the oscilloscope would just be displaying some like constant voltage across that capacitor forever and ever and ever. And then you short it, and then suddenly it would go to zero, and you go, well, I didn't see it. I didn't see it happen because it would happen in real time. So basically, triggering kind of when you put an oscilloscope in triggering mode, what it does is it kind of captures that moment when the voltage drops below a certain amount. Okay, so I actually have a video which doesn't quite show the triggering, but it shows the next step, which is, okay, now that you've got the oscilloscope actually showing that red curve, and you would see that right on the screen of the oscilloscope. Once you've got that, how can you measure what the time constant is? And what you could do is you could take two different times, and you got two different voltages at those two different times, and then using those two different times and those two different voltages, you would be able to actually calculate what the time constant is from the oscilloscope reading. And once you've got that, is that equal to RC? Because after all, you put R in the circuit and you put C in the circuit. So theoretically, you could just multiply R and C and you would get tau. Experimentally, you can measure tau by looking at two different times off of the oscilloscope capture, and you would say, okay, are the two taus equal to one another? Yes or no? And if they are, well, then the theory is verified. If they're not, well, then something went wrong. Okay, either in the theory or in the experiment. Now, unfortunately, I would love to have had even just one capture where there was actually numbers and people did numbers, and they did. What I have is someone showing this very diagram, but they just pointed out qualitatively. So unfortunately, in this part of the lab, you won't actually be able to verify this equation experimentally the way we would have in the lab. But you know what? That's okay. We will be doing this theory in class anyhow. Okay, and just to tell you, I've done this experiment before, and it turns out extremely well. Okay, I mean, you almost get exactly the RC value. There's very little experimental error. Okay, so let me look in the chat here if there's any questions, because this is basically everything for the theory of the lab. At this point, I would have let you guys go, but let's go. Let me look. Are there any questions? No, it doesn't seem like there are any questions. Okay, so you know what? Let's go to our course site again here, and let me show you what I expect for a write-up. Oh, I should just mention one other thing. There is a third part to the lab, and it was using integrated circuits. There really was no theory. We're not going to do that. Let me just tell you what it was about. There really was no theory about this, but integrated circuits are just kind of like many capacitors and resistors all hooked up inside of a circuit already built like that. And so you can see there a picture of an integrated circuit. And what we were going to do with it is we were just going to plug it in and basically just have a little LED flash on and off. Okay, so we were going to build this circuit, and you would have this LED, and it would just like turn on and off. Okay, and by changing the variable resistor here, you would actually have it be able to flash on and off at different rates. But you know, it was more like a fun thing to do rather than something which was you know, something that which gives you any new theory. So there was no new physics insight from this. It was just kind of, like I said, a fun thing to do. But we're going to skip that. Okay, so let's go back to the bottom here. So what we're looking at is my summary and then some YouTube videos that I expect you to watch before you do your write-up. All right, let's look at the summary of the lab. Okay, and so you know, it's kind of a summary of what I've already said so far. You know, like in your introduction, what you should be writing is why are you doing this? Like, what's the purpose of this lab? And you know, the actual lab write-up had more because it had the integrated circuit. But for us, there's just two things that we're showing. One is that the voltage drop across all the resistors in series is just basically equal to the voltage applied to the by a power supply. Okay, so in the examples that I gave you, if you've got a 10-volt battery and then you got a bunch of series resistors in series, if you were to measure the voltage drop across each of the resistors and add them all up, you would find that that's got to equal to 10 volts. Okay, a little bit more than that though. You know, in addition to that, you can also, if you know the size of the resistors, you can actually determine, You can actually calculate what the voltage drop will be across each one of them, and then of course adding them all up should add up to the voltage of the power supply or battery, whatever you're using. So that's purpose number one. And the second thing that we did in the lab is we're actually showing that the charge on the capacitor in an RC circuit will either exponentially grow, that's if you're charging it with the battery, or exponentially decay if you're discharging it. Okay, so it's that the word exponential is important. Okay, so we saw exponential decay with the damped harmonic oscillator. All right, so this is the exact same thing. It's an exponential decay in the amount of charge. It'll actually decrease over time, but decrease over time exponentially, not linearly. Okay, so the charge on the capacitor, of an RC circuit will exponentially decay over time, and that exponential decay is characterized by a time called a certain constant called the time constant. Okay, so experimentally, in the experimental section, what do I want you to describe? Well, don't describe a multimeter again. You kind of did that already. That was last lab. But describe how you would use the multimeter to measure the voltage across resistors in series. You may want to do that after you watch the videos, because you'll see. I forget the professor's name, but he does an experiment. He'll actually use the multimeter, and you can see the numbers. He's got all the numbers there, and he doesn't do any of the calculations for you, which is perfect, because he just does the experiment, and then you're expected to do the calculations afterwards. I mean, it's ideal. It's exactly what I would have done if I were to produce a video for you guys to analyze. Okay, and so that's number one. Describe how you would use a multimeter to measure voltage drop across resistors in a circuit. And then how would you use an oscilloscope to do two things? Show that the charge in the capacitor exponentially grows or decays, and you'll see that in one of the videos. Okay, so how would you use an oscilloscope to do that? And also, how do you measure the time constant? And I have a YouTube video which is specifically aimed at that. Now there's a lot of information in that, so you really want to key in into how it's done without like actually doing numerical example how it's done. And you basically have to pick two times, and there are two voltages at two different times, and by fitting the exponential to those two voltages at the two different times, you're able to get the time constant. Okay, and so he does that actually in that video. All right, and the results, for the I guess his name was Letzum. Okay, so Dr. Clyde Letzum, he actually does this measurement, and in that video you will actually see the resistor values, and you will actually see the voltages that he measures. So what I want you to do in your results section is use the theory that I just showed you to calculate the voltage drops that you would get across the three resistors, and see if it's what Dr. Letzum got when he actually did the measurements. Okay, so basically you're going to do it theoretically using the three resistor values, and you'll see those values in the video, and then you'll calculate the voltages and then compare them to what he got. They're not perfect. It's a little off. I did it, and it's a little off, but it's pretty good. It's pretty good. So so that's basically for number one here, for the voltage drops across resistors. And then for number two, like I said, I couldn't find anything where there were numbers, where you could actually read the numbers off the oscilloscope. There are even these virtual simulations of oscilloscopes online, but they're not that good, and they don't do RC circuits. So I just couldn't find anything. So basically for number two here with the exponential decay, just qualitatively describe what you saw in the video that shows the exponential decay and the exponential growth on the circuit. The guy basically has a little switch, and he closes the switch, and you can see the thing charge up. He opens the switch, and you can see it charge down. And it's got the oscilloscope trace has exactly the characteristic shapes that I showed you just a minute ago. Okay, and so there you go. That's the lab for this week. And let me look in the chat here. If you've got any questions, ask now. The calculations here, I lost the trace again. The calculations that I'm talking about right in here, okay, I mean, you should be able to figure them out, but if you can't, you can always catch me in one of the Google Hangouts, or just email me, and I can give you some hints, okay, how to do it. It's not that hard, and like I said, by next week, we'll have a lot of this theory done in class anyhow. Okay, so let me see any questions. All right, how many people are viewing? It looks like 12 people are viewing. Okay, so I'm going to end the lecture here, and that's it. So try to hand in your labs like you would if we were physically in class. So last week's lab is due today, okay? And when I get a lab, I will email you back and say, hey, I got it. If you don't see me emailing you back, I got it, then maybe something went wrong. You know, every once in a while, a mail system will say, oh, this attachment looks like it's a virus. I'm just going to drop it, and then I may not get it. Okay. So if I don't get a lab from you, then I'm going to email you and go, hey, you know, I didn't get this lab, hand it in, and so on. And if you wait a few minutes, I'm going to email you the link. I'm going to email everyone the link to this lab description. Okay. Let me look again to see if there's any questions in the chat. Oh, it looks like there's something here. Oh, no, there isn't. I'm sorry. I just scrolled wrong. All right, guys. Well, hang in there and bye-bye.